Great to be here. Right, so I'm just pretty much going to give an overview of what we're doing at Bleximo. But before I start, I've kind of given this introduction many times for those of you who've seen this talk, but I will remind people that the Apollo guidance computer that powered the mission that got us to the moon actually only had a 2 megahertz clock and about 2 kilobytes of memory, right? And that's trivial by any computing standards today, but that was really enough to get us to the moon, and that was a pretty complicated task. Of course, the reason that was enough is because people they were highly focused on what they needed to do, and they were limited by resources, but they thought very closely on how to design the software that was going to run based on what the hardware could do. So the reason we bring this up is because this is really what Bleximo's vision is. Bleximo was founded as an application-specific quantum computing company. The hardware that we use is based on superconducting qubits, but the idea is that if we integrate the hardware design with the algorithms that are going to be run on it, we can deliver better performance. And I'll give an overview. I think for some reason there's timings on there. But really, we want to start with the applications, and then from there, think about what are the hardware architecture and also the systems around the hardware that are needed in order to deliver the best possible performance for that particular application. And so, what are some reasons that we think this is a fruitful approach? Well, one of the main ones is speed. Ultimately, with or without fault tolerance, if you design a specific hardware and you narrow the scope to kind of improve the performance only on delivering on running certain algorithms, we can cut the execution time of those algorithms quite a bit through various techniques, and some of those techniques might be in the software layer itself, like the compilation scheme, and some of them might be in, for example, tuning specific gates and trying to reduce the execution time of those gates. The other, and probably equally important, especially in the next decade or so, is the lower complexity and costs of the system that you're building. Quantum computers are still very expensive to build. That's going to require, and they're going to require a lot of iterations in order to get to the point where they deliver true value. And the cheaper we make this and the easier to kind of iterate on those devices, probably the sooner we'll get to the point that we want to achieve. And then finally it's important to mention higher IP security. If you're an end user specifically and you come up with a new algorithm, it's typically pretty hard to protect that algorithm unless you keep it a secret. But if you integrate your algorithm with a specific hardware architecture, it's easier to patent for, if you're interested in that. And also, of course, harder to reverse engineer. It doesn't, having the algorithm may not be sufficient. So this is essentially an overview of our approach. The idea is to start with a customer problem. That problem, in turn, can be solved by normally a variety of algorithms. We, of course, narrow down to to kind of the most promising ones. That kind of determines ultimately a quantum circuit, and that quantum circuit in turn has, it can be expressed in many different ways. And by working with the actual hardware and processor team, these algorithms can in turn determine a specific set of hardware requirements that we try to achieve, and we kind of try to focus on those requirements without building extra bells and whistles, let's say. I mean, not that bells and whistles are bad. And then ultimately, that's supposed to deliver faster run times and better execution fidelities for that specific algorithm. Now, of course, a natural question that comes up is, okay, are you going to build a chip for every single application? That's not the case. And then another question is, do those chips have dramatically different requirements? It's going to be really expensive. And going to be even harder to drive down the cost, which is, of course, one of the goals here. And in order to do that, we think very closely about the actual platform that these superconducting systems have to run in. And that, of course, includes the cryogenic environment, the shielding and packaging technology, the control systems and classical hardware that's needed to run this, and even the software that's going on that on the entire system. So, one of the focus areas that we have right now is making a platform that allows for new and different kind of processor architectures to be tested quickly. I'll talk more about this platform in a little bit, but one thing I want to emphasize is that while the actual chip layout and the gates that are optimized on that chip might be different for different applications, the entire system would be able to run any of these. And so, okay, in order to achieve that goal, like I said, there's lots of different aspects in a superconducting quantum computing architecture, and we have kind of projects around every single one of those, or at least a lot of those. One of these is to improve processor stability. In order to design processors, to design different processor architectures, we also need to have good software to lay out that processor and try to predict its properties well enough to also reduce costs when manufacturing. We need good compilation schemes to get good gates. We need to ultimately integrate all those into that's what we call the co-design methodology. And in order to deliver real value, we need big systems. And we need to scale, so I'll talk a little bit about that. And finally, there's the control systems that are also quite expensive when building one of these platforms. So here I'm showing a video of the processor team, and the idea is to have as much automation as possible when designing an actual processor. So here it's actually a 4-qubit processor, and we essentially have a library of components that have been pre-optimized in some way and get put together into a chip, and then that the actual kind of properties of the chip are computed and then estimated, and we can move things around, change the sizes and so on in order to try to come up with a chip that has good properties and can deliver hopefully better performance when deployed. Another example, so this is a purely software example. This is the very bare bones algorithm that does Monte Carlo simulation on a quantum computer. It's been improved since this picture, but one of the steps, and okay, Monte Carlo simulation can be used for a lot of things, including pricing of derivatives. And what we did here is took the simplest possible derivative you can think of, which is a single period European call option. There's one movement, the price goes up or down. And one of the steps in that algorithm involves kind of repeating a circuit that kind of encodes let's say the properties of that option. And you have to repeat that many times, and that the number of times you repeat it more or less determines the precision. And if you just construct that circuit in a very standard way, kind of following the paper, you kind of get to the circuit that I have above. But it turns out that because this derivative is so simple, you can actually, this circuit is equivalent to this smaller circuit here. This is not like a generic thing. It's not like a novel compilation scheme or anything like that. It's just to illustrate the point that if you kind of fine-tune into specific applications or algorithms, you can dramatically reduce the circuit depth purely through software means. So this is another way in which we envision kind of the application-specific approach improving algorithms in general in quantum computing. Okay, so another aspect that I mentioned is the cryogenic platform. So this is a dilution refrigerator. It cools the chip down, and there's a bunch of cables here that are used to control and read out the qubits. But you also need to isolate that the processor from environmental noise. And in order to do so, we develop our own kind of shielding and packaging technology. You can see You can see that at the bottom. We actually sell these to academic institutions and national labs. And I'll show, here, I'll show the next slide. I accidentally went back. This is a test we did, with our partners at Berkeley. And what we did here is this same exact chip, the same exact processor, has 8 qubits. It was cooled down in 4 different scenarios, one with no shielding, one with, and 2 and 3 would be with the shielding that the lab was already using, and then the final one was with the solution that we have and we sell. And shouldn't be going forward. And you can see here that pretty much across every single qubit, the T1 times, the coherence times for those qubits improved quite dramatically. So this is just another aspect in which we emphasize that in order to deliver good performance in these, at least in these quantum computing architectures, you really need to worry about the entire system, and it's not just about the processor itself. And then before I talk about the next aspect, I also want to highlight one thing that we've announced this week, which is the Rubicon platform. If you want more information on that, please go to our booth. But what we are envisioning is essentially reimagining the dilution refrigerator, at least for testing small chips or some material science experiments. We want to actually make the dilution refrigerator as small as possible, fit in a small rack, integrate all the control electronics into that system so that you can buy one solution, put it in a lab or put it in an academic institution, and run tests at a much faster pace than you would have to do every time you need to replace the sample that you put in the dilution refrigerator. So if you want more information, please go visit our booth. There's also some more information online on a Medium post. And then finally, the last thing I want to emphasize is scalability. This is just a picture of a standard dilution refrigerator with all the cables kind of going down in order to control and read out qubits. And obviously those cables also generate heat when you're sending signals down, and that kind of limits the size of the processor that you would be able to control on a system like this. So one solution is to build bigger dilution refrigerators, which will likely also be needed, but if we could replace these cables with something that heats the system much less, then in principle, we could fit a larger processor and preserve good kind of fidelities in this same dilution refrigerator. So one of the projects that we have going on is essentially a photonic control system, right? So you, instead of sending RF down, you'd send photons down, use a photodetecting chip that converts those photons into RF right by the actual qubit chip. And if you can do that, there are lots of techniques that would allow you to kind of control a much larger number of qubits without heating the system up. And so ultimately, we see that as a path to scalability, because not only would you fit much larger chips inside, but it's also a way to connect multiple chips if you can also get the photonic kind of system to connect between chips. Now that's kind of course, it would be the next step. But ultimately, if you want to build large systems, we do need to improve the cryogenic environment as well. And so this is just a kind of a very high-level picture of how we see different chips being interconnected with these photonic controls. That's really it. I'll leave it at that, and I'll answer questions if anyone has any.
Okay, we have a question down here.
Perhaps I missed it. I came in a minute late. When you say hybrid, you're hybriding supercomputing? I mean, not supercomputing, the transmon with photonics? What's the hybrid?
So, well, if you're talking about the photonic part, it's still the actual quantum computer is a superconducting chip. It's transmons, but you would use photons to get the information that you're essentially your gates, right? Like that's how you would eventually translate those onto the chip.
So it's photonics and
yeah, there are that to some extent, yes, but it's not like don't think about it as the photonics that you might see from a photonic quantum computing company. So the quantum computation is not happening using the photons.
It's following. It's very interesting. Is anyone else doing this, or it seems somewhat unique? Are you guys?
I think that as a company that I haven't seen other companies do this. Of course, the idea itself about using photodetectors to convert photons into RF has been done in academia before.
Okay.
But this is the kind of in terms of integrating into the system. I do not know of any other company that is doing that.
Thank you.
Yeah.
Okay, another question.
So your vision on co-design software hardware was mentioned, but all these individual components are improvement by itself, and I don't see a total flow of design of entire system or feedback with software. This kind of thing I haven't.
Yeah, that's right. You didn't see it because I didn't present it. To be honest, that's a missing part. That's an ongoing work. The real vision is we do need to integrate these things, and even by themselves, improving each individual component is kind of improving the entire system. We have already, there's evidence not just from us, but from anyone in doing superconducting qubits that noise doesn't just come from one specific thing, right? It's not just a fab process that creates noise. It's not just control systems. It's not just environmental isolation. So all of these things are important. Now, ultimately, like the actual architectures to run specific algorithms, I haven't presented that, and we don't have those yet. But mostly because it's a little too early to do that, right? But at least on hardware, right? We do have projects in terms of like the software and algorithm portion of it, like they're of the flavor of the kind of derivative pricing that I showed. But in terms of like the full integration, the best thing I can say is the Rubicon announcement, this new product. It is one hardware platform that has everything kind of integrated together, but I wouldn't say that that's already an application-specific chip. It's more an application-specific, it's more an integrated platform that is in fact generic to any kind of cryogenic experiment that you might want to run within some constraints.
Okay, one more question over here.
Okay, so you you showed that with your shielding, you can get T1s that are like way higher than what you get without your shielding. Mm-hmm. So I'm wondering, do you have like the ambition to essentially sell your shielding technology, as standalone hardware for other companies or even outside of the quantum computing space?
So to academics, we're already doing that. To other companies, we have not done that, but I wouldn't rule it out. I think that, at least my personal opinion is that, the whole ecosystem is sufficiently early that probably benefits everyone from other people kind of improving their own system. So if any other company is interested in this, I would be happy to chat about it, but we haven't done that yet.